All right, and lastly, we have example number 5. Again, we are given a reaction, so I'm gonna write out the reaction. I have H2 gas plus F2 gas forming HF, also a gas. I'm told that we have an initial concentration of H2 and F2, and we have no initial concentration of HF. So to find the concentration of H2, I have to take the value of moles and divide it by liters. In this case, I'm going to get 1.000 moles per liter. In the case of F2, I'm taking the moles, 6.000 divided by 3.000, which will give me 2.000 moles per liter. HF, my initial concentration is 0. So that was my I. In order to take a look at my C, which is my change, I have to take a look at my balanced equation. So I just realized that this reaction is not balanced. I'm going to put a 2 there in order to balance it. And because H2 and F2 have an initial concentration, I know that that is going to decrease over time. So the value of the change can be signified by X. So it's going to be minus X for both H2 and F2. Because HF started off having a concentration of 0, while it's reaching equilibrium, it's going to gain. Right? So when it's gaining, it's going to gain according to the coefficient, so plus 2x. And at equilibrium, I'm going to write my expression as 1.000 minus x. F2 is going to be 2.000 minus x, and HF is going to be 2x. Again, I'm going to go off of this to make or write my K formula, which is, so K is equal to H, the concentration of HF squared, because it has a coefficient of 2, divided by the concentration of H2 times the concentration of F2. Okay, I'm going to sub in all of my expressions and the numbers that I know. I am given a K value in the question, which is 1.15 times 10 to the power of 2. And then I'm going to sub in all of the numbers. So 2x squared is going to be 4x squared divided by 1.000 minus x times 2.000 minus x. And again, I need to solve for x. When I divide my concentrations by my K value, when I do 1 divided by 1.15 times 10 to the power of 2, I do not get anything above 500, which means that I cannot make the assumption, which means that I'm going to have to do this the long way. I have to keep my minus x here for both initial concentrations. So eventually what I'm going to do is I'm going to multiply this out and simplify it so that I can get it into a form that I can solve for. And that form is going to look like the quadratic equation. Because we've done so much practice already, I'm assuming that you know how to do that. So I'm not going to explain this in so much detail, but what's going to end up happening when I multiply this out is I'm going to get it into the form of the quadratic equation. 230 minus 345x plus 111x squared is equal to 0. And because we're so familiar with our quadratic equation format, we should already know that this is A, this is B, and this is C. Knowing that, we can plug it into our quadratic equation, negative b plus or minus square root of b squared minus 4ac over 2a. And when I solve for x, I'm going to get two different values. So I first get 0.96838, that's the not rounded value, and I also get x is equal to 2.139. Now, this is like an example that we did earlier where I've got two positive values, but I have to think about which of these makes sense. So comparing it to the initial concentrations, I've got initial concentration of 1 and of 2. Now I have to ask myself which of these does not belong, which of these does not make sense. And the second one, the one where x is equal to 2.139, really doesn't make any sense. And this doesn't make any sense because this is more than the initial concentration, right? Which means that this cannot be our value of x, which means that this is going to be the x value that I choose. So using this, I can solve for the concentration of HF and H2 and F2. So the concentration of HF is 1 minus 0.96. I'm going to use the full number, and that's going to give me 3.20 times 10 to the power of negative 2 moles per liter. My concentration of H2 is going to be, oh, I messed that up for sure. So this is going to be my concentration of H2, and this is going to be my concentration of HF. And this is going to be my concentration of F2. Okay, so for H2, I know that it's 1 minus X, which gives me the concentration of H2 at equilibrium. At F2, my concentration at equilibrium is 2 minus 0.96, or 2 minus the X value, which will give me 1.03 moles per liter. And for HF, it's 2 times X, which is 2 times 0.96, etc., which will give me 1.94 moles per liter. So that is how you would use the K constant as well as the ICE table to figure out the equilibrium concentrations for a bunch of different reactions. So that was example number 5. Hopefully you have a good understanding of it. There's a bunch of practice questions that you can do in the homework to make sure that you really understand this.